Everybody, thanks for coming out. Today we have Dr. Lijie Zhang from Washington State University. He's a postdoctoral researcher, started in 2025, and works on land-atmosphere interactions and large-eddy simulations with a research focus on energy balance closure, atmospheric dynamics, and surface processes that govern the exchange of water and energy between land and the atmosphere. Dr. Zhang earned his PhD in meteorology from the University of Bonn, with his doctoral research conducted at Research Center of Jülich in Germany. Please join me in welcoming Lijie. Thank you.
Yes. Good afternoon, everyone. I'm very excited to be invited to give my first seminar of my life at NCAR. And thanks, Pat, for the introductions. With these opportunities, I would like to present the ongoing project about examining the influence of the heterogeneous forest canopies on the shallow convections. So I will start from these figures. This figure shows the domain and grid size for the different models here. From the largest one, we have the global climate models, which have a grid scale of 100 kilometers. Then we find the numerical weather predicts here towards to the age of kilometer scales. We have the regional climate models here, and then you can increase the grid size to the larger simulations domains. Then you can even do the direct numerical weather simulations here. We found that with the increase of the model grid sizes, normally we need to reduce the model domain sizes. And if you want to keep the domain sizes while increase the model grid sizes, you need a lot of things. You need the growing computational powers because it's not just horizontally 2 times. You also need to increase the temporal resolutions here. And you need a lot of higher resolution inputs for the boundary conditions, for the initial conditions, and for the forcing data. Most important, you need the complete physical processes. A lot of things was just parameterized in the causal resolution models here, but when you increased the grid sizes, you might need to resolve all those processes and, for example, the canopy atmosphere exchange here. These figures show the complex interactions of the atmosphere with the land surfaces. The land surface is always heterogeneous at different scales with the different land covers. You might have the different soil moistures here, for example, and even you have the same income radiation to the surfaces. They might redistribute the energies differently. So, for example, in these figures, at the wet regions, you tend to have more latent fluxes, and at the dry areas, you tend to have more sensible fluxes. So at the dry area, the air temperature should be higher, and you might induce some updrifts in those dry areas. And in the wet regions, not necessary to be the downdrifts, but you must have some downward atmosphere motions, maybe from the compensations. Then with the increase of the boundary layer, especially when you exceed the height of the lifted condensation levels, then the shallow convections forms. On the right side is just configurations of how the COM subgrid hierarchies tell us using those tile-based approaches to represent land surface heterogeneities in the climate models at the moment. They calculate different land use or land planet function types for the ratio of that grid cell. Then you average based on the aerial ratios then. So by leveraging these opportunities, I will also briefly introduce my previous work with idealized large-eddy simulations with soil moisture heterogeneities to give you a feeling how those land surface heterogeneities impact the atmosphere. Then the project I'm working on now is start from June 2025, I think. And then it's still ongoing, so I will give you introduce some collected data from the measurement, from the in situ, from the field, from the satellite, and some mesoscale simulations were already done yet. So, if we have a flat river corridor that is represented by the wet soils in the middle and very dry at the edge, in larger simulations, we set the grid size of 50 meters times 50 meters, and this is the double periodic boundary conditions. With this kind of setup of the soil moisture, if you give a constant income radiation to these domains, what's going on there? Because we have the wet soils and the dry soils. It's exactly what happens as the previous figures I showed. At the dry area, you might have some updrifts. And at the wet area, you might have some downward motions of the atmosphere. So you got this. This is a vertical cross-section from this Y. The directions of the mesoscale vertical wind for the left one. So red means goes up, and blue means goes down. Then on the right side is it's for the horizontal wind. So you form this kind of circulations here. And this patterns has been reported many times in the literatures. And what happens if we have some large scale forces? For example, we add some ambient winds, and the winds can have the different directions and the different wind speed. For example, here I set the wind speed ranges from 0 to 60 meters per second. Then you got this. When the wind is parallel to the river, the structure persists no matter how fast the background wind you imposed. But when the wind is perpendicular to these rivers, then the structure removed at a certain moment when the wind speed is strong enough. Because from this setup of the larger simulations, it's kind of one-dimensional heterogeneous, right? Then we extend these patterns to the two-dimensional. Here I'm using the classic checkboard patterns of the soil moisture. Here the dark one is actually the dry for the lower soil moisture, and the lighter one is for the wet soils. And the grid size is again with 50 meters times 50 meters. But the patches, those patches have the different scales, ranges from 2.4 kilometers, 1.2 kilometers, 600 meters, down to 50 meters. And you got this. The first figure is the vertical wind. Second one is the kinetic heat fluxes, the turbulent heat fluxes. And third one, the surface heat fluxes. And what we found here is that the structures in the atmosphere aligns pretty well when the scale is large enough to the surfaces. But when the heterogeneous scale was decreasing to certain levels, then those structures is not aligned with the land surface anymore. Then the third case study is we set the same soil moistures, but with the different standard deviations, also with the different spectral patterns. So this is what the larger simulation gives us. Like even you have the same, exactly same mean soil moisture values, you have the different wind speed, and most important, you have the different liquid water passes. So all this idealized larger simulation just to give you a feeling that the land surface heterogeneity really plays a role to the atmosphere. Even with just the most simple soil moisture one, and we have a lot of different heterogeneity stuff things. So now let's talk about this ongoing project to examine the influence of the heterogeneous forest canopies on shallow convections. Because this topic is really matches my background and my interest. So I will start from this figure. This figure shows the national land cover databases. So US was covered 30% of the forest, and especially on the southeast regions, especially during the spring and summer seasons, this synoptic scale forces is often very weak. That means that area was like, high pressure dominated. And the forests will strongly influences the boundary layer growths and could generate those locally forced shallow convections. And the research question here is that how does this canopy heterogeneity affect the locally forced shallow convections? And to study on those research questions, we're using the data from the ARM Bankhead Bankhead National Forest site. This BNF site was located north of the Alabama. And if you zoom in this area, we have this M1 site, which is the main site in the forest. And west, to the 1 kilometers west of this main site, we have the S10 site. The S10 site is a newly installed flux towers, have 140 feet, which is 43 meters. And our instrument was mainly installed on the S10 site, and we have other 3 sites outside the forest. So this is the schematic diagram of the eddy-covariance setup at the S10 site. So there are 3 eddy-covariance measurements on the tower. At the top of the tower, slightly above the canopy and below the canopy. And our groups from the Washington State University, we installed 5 additional eddy-covariance measurements systems on the tower. From the above to bottom is 31.7 meters, 26 meters, 16, 7.85, and the lowest one is below the canopy. Here I also show some figures about taken from the cameras installed on the tower. The cameras at the top from the west, southwest, and also the camera images from southwest at the 4 meters. So till now, we have created eddy-covariance workflows, like including all this pre-processing to remove the spikes, noises, or to do the double rotation things. And this workflow can calculate the fluxes, like the sensible length fluxes, the momentum fluxes, or the carbon dioxide. And this workflow can also do some advanced analysis, for example, like the choroid analysis or the spectral analysis. We have collected a lot of data from the site. For example, the main site have ceilometers, radio sound, which have like 4 or 5 times per day. They have LiDARs, they have radiometers. They also have the surface meteorological instrumentations and soil sensors, etc. Also at the S10 site, they have the sky imagers, they have the discrete temperature sensors. They also have these laser disdrometers to provide the rainfall information. We also collected some synoptic scale maps to filter out the days that is dominated by the high pressure. And the last thing is we do the WRF simulations. Currently, we just do the mesoscale simulations at 1 kilometers grid size, and the output, the data can be used to foresee the higher spatial resolutions in the larger simulations. Okay, this slide is to demonstrate the data collected by the eddy-covariances from the 5 eddy-covariance data. So you see a clear dynamics of the sensible fluxes and the lengthening fluxes. And here, these vertical discretizations can also be displayed here. For example, this orange colors is represent the lowest level, which is below the canopy, and those two dark blue colors is represent the site above the canopy. And you can see here that the lengthening flux is below the canopy is much lower than above the canopies. On right side, I show the dynamic of the temperature. Also, the air temperature, especially at night, increases with the height within canopies. But at the daytime, they might have quite similar values. The last one is for the carbon dioxide. Within the canopy, especially at night, when there's no photosynthesis, the carbon dioxide have higher densities in the lower of the canopy. Okay, next slides, I'm gonna show you how we did the choroid analysis. When we calculate the eddy-covariances, we're using the covariances, which is the combinations of the fluctuation of 2 scalars. And actually, there are 4 combinations. Both of them are positive, both of them are negative, or when the vertical wind is positive but the horizontal wind is negative, we define it as the ejection here, as a Q2. When the vertical wind is negative, and the horizontal one is positive, then we define it as Q4. So when the quadrant 2 or the ejection is dominating the area, then means the atmosphere is dominated by the upward. But when this quadrant 4, the sweep is dominated, then it's like sweep down. So here I calculate the differences of these two quadrants, Q2 minus Q4. We have this dashed line here to represent 0. When it's positive, for example, those yellow triangle colors represent the lowest layer at the bottom of the tower. And you see a lot of values are positive, means like they are going up. But for those dark colors above the canopy, it's dominated by the sweeps, means the air above the canopy was actually sweeping into the canopies. On the right side is the time fractions. So it's like this updraft is very strong, but with very narrow or less time fractions. But for the sweeps, it's much weaker, and you have larger time fractions. This slide is to demonstrate the discrete temperature sensors. Since we already have 5 layers of the eddy-covariance measurements, we also have the measure the air temperatures. So I made a comparisons here. Below is the discrete temperature sensors. As you can see here, it's a very high spatial and temporal resolutions, especially after the sunrise. Then you can see the patterns like it's heated up here, and this DTS can provide a fan scale temperature gradients within the canopy, and those data can be used to validate the canopy models if we want to run that coupled with larger simulations. For example, the M canopy, which I will introduce later. Now we're using these synoptic maps to filter out some days which is high pressure dominated on the southeast of the United States. Our location is located here, Alabama, and for both June 3rd and June 4th, it's dominated by the high pressure with a value around 1016 here. So these 2 days going to be used at the case studies at this moment. Now I'm going to show you some clouds. The left one is from the GOOSE geostationary satellite data images with the cloud cover data. The right side is the sky images at the site. So you can see the clouds is from the left is from the top, and the right one is from the bottom. So the time here is actually using UTC. On the right side, you can see the clouds actually appears around 9 or 10 a.m. in the morning. And on the left side, those dark blue, show it again. Those dark blues are 100% cloud, and light blue is like the marked as probably cloud, and those light green is shows like probably clear. Then you see in the north of Alabama, the clouds appears also at not now. Yes, roughly here now it appears those clouds. So also around like 9 or 10 a.m. Besides these 2 data sets, we have the ceilometers, which can provide the cloud-based height at the M1 side. So I made a comparisons of those cloud categories by the 2 different data sets with the GOOSE and with the ceilometers. The first one is for 4 days. That is marked with the different color bars. When it's dark blue, it should be cloud, and when it's light blue, it should be probably cloud. The second one for ceilometers, I set the threshold of the cloud base height lower than 5,000 to just filter out those low-level clouds. Because this is more probably the shallow convections, and on the third figures is the combinations. When it's dark blue, it means both data sets says, oh, this moment is a cloud. When it's light blue, it means the ceilometer says this cloud, but the satellite says this probably clear. And when this light blue shows here, there's only the satellite says there's cloud, but the accelerometers didn't figure it out. So from these figures, we say the onset of the clouds, for example, especially for the June 3rd and June 4th, was roughly around 9 or 10 a.m. in the mornings. And this figure shows the boundary layer height compared with the lift condensation levels and also the cloud-based height. Those gray areas is the moment when the boundary layer height is larger than those lifted condensation levels. And you can see here for, I think the second figure B is June 3rd, C is June 4th, and the clouds will always appear like 1 or 2 hours after the boundary layer height is higher than the lifted condensation levels. Then you have these black dots which represent the cloud-based height at a height of roughly 2,000 meters. Okay. Now we move to the WRF. So on this figure shows the workflow of the WRF. The WRF consists of two parts, the pre-processing system, WPS, and the WRF itself. And this WPS contains two parts. The first one is you need the static geographic data set, which is mainly to provide those lower boundary conditions. And you also need those meteorological data, for example, to provide those lateral boundary conditions or those initial conditions and also the forcings for the model. Here we're using the high resolution rapid refresh HER data, which has 3 kilometers and can provide hourly data. In these figures, I made comparisons with the HER data and the MODIS land surface temperature. Here I show the time at a local time here. The left panels is for the June 3rd and the right ones for June 4th. The MODIS data is contaminated a lot by the existence of the clouds. So you have to see a lot of halo data here. There's no data here. The comparison shows slightly overestimated by the HER data in these regions. Yeah, but in general, the difference is less than 1 or 2 Kelvin. And I also made a comparison of the WRF or the HER data with the soil moisture, because even though it's a mesoscale circulations, we just run for 24 hours. So we assume the soil moisture does not change a lot if there's no precipitations. So the first one is the soil moistures from the HER data. I selected the layer 3, which is roughly 10 centimeters, 5 to 10 centimeters, which is comparable to the SMAP data, which using the L band, so you can penetrate to roughly 5 centimeters. It's clear that the HER data is slightly underestimated the soil moistures compared to the SMAP data here. The right ones show the differences. Okay, I also, in the WRF, they do have those default setups. So if you just give the pass to the WRF, and the WRF can generate using those default setups. They have, but those data sets are pretty old, which maybe sourced back to decades. And on the right side is the live area index downloaded from those MODIS data. For example, the first rows is for the April of this year. Then we have the data from the May and from the June. As you can see here, they are quite similar, with similar patterns, similar structures, but definitely on the right side you have the higher, how to say, they share the same grid sizes here, but the right side have the higher details, I would say. Okay, then I'm gonna show you some output from our WRF simulations. So this is the cloud-based height. Yes. So those red colors are the clouds, the cloud-based height larger than higher than 5 kilometers, and those colorful clouds was low-level clouds generated by the models here. And you have, go again. You have similar patterns that you start from the northwest here, and you have some locally shallow convections in the Alabama. But the problem here is the clouds was start generated at a time around 2 or 3 p.m. But from measurements, the clouds was already formed in the early mornings in the transition period at 9 or 10 a.m. here. So we found some mismatches in the existence of the clouds compared to the measurements. We also have those measurements for the radiations and also for the heat fluxes from the eddy-covariance. So I made comparisons with at the point scale. So the left side shows the red color shows the WRF simulations, because before 2 p.m. there's no clouds. So all those sites shows almost a perfect dynamics of those shortwave income radiations. Then when the clouds was formed after 2 p.m., then you have see those kind of fluctuations due to the existence of the clouds. However, for the black ones, for the measurements, the clouds or those fluctuations was already started at as early as 9 or 10 a.m. in the mornings. And this is also a signal, shows there's clouds existed at that moment. And this mismatches was observed here. On the right side is comparisons of the heat fluxes. The red color represents the sensibility fluxes, and the red color represents the lengthened fluxes. And from here, you can say, luckily, this the figure B is from the forest side S10, and especially after the clouds was appears, you have a pretty good agreement with the both sensible and lengthened fluxes here. And also you have a very good agreement with the side S30 that the lengthened flux can reach to 650 watt per square meter, and you have this sensible fluxes slightly lower, but you missed these peak values here. And also for this S40, the performance is not very good, that the WRF is slightly overestimated the lengthened fluxes while underestimate the sensible fluxes. Also at the M1 side, we have those vertical yeah, go ahead.
Sorry, I missed on the last plot.
Oh, sorry. Yeah.
Were those roads different days?
No, it's for the same days, but for different sites. We have, yeah, we have 5 sites.
Yeah, okay. Thank you.
Okay, and this figure shows the vertical profile of the potential temperature, the upper one, and the specific humidities at the M1 site. This is for only 1 day, June 4th, and to the left to the right is the days for 6 a.m., 9 a.m., 12, 15, 18, and 21, and all these are local time already. Here, the blue colors represent the WRF simulations with the default setup, and the light blue is the WRF simulations with the updated live area indexes. Then we also have the red one from the HER data and the black ones from measurements. For the potential temperatures, they matched quite well, and they also captured the boundary layer height here. However, for the specific humidities, that the HER data was especially in the boundary layer, it was slightly underestimated of the specific humidities compared to the sound measurement. However, the WRF can correct these mismatches and even cause some slightly overestimation of these specific humidities. And with time keep developed, for example, at noon, this WRF is overestimate the specific humidities compared to the measurements here, and also slightly the boundary layer structure is not that clear compared to the measurements at these locations here. Yeah. So that's the current status of our simulations. And our next step is to run those nested larger simulations, start to download downscaling from those 1 kilometers grade to 100 meters, then finally to 10 meters, and with multi-layer canopy models named M-Canopy, which was developed by the Washington State University group in 2019. And our groups also have this GPU-based large simulation called fast eddies. Here I will very briefly introduce these M-canopies that they developed. These canopy models that have several modules. For example, have the radiative transform modules to calculate the flux balances at each canopy layers. They also have these momentum drag modules to incorporate this the momental scales. So, and this model has already been implemented in large simulation, WRF. At this moment, all you need is just an input file for the vertical profile of the live area index, or let's say live area density. So this is the update of this project. And I'm not just here to demonstrate some data or show some progress, but also like to seek some suggestions or advices or comments. Thank you.
Done. All right. Thank you so much, Lee. Yeah, and at this point, we'll take any questions.
Thanks for your talk. So I wonder when you compare with the SMAP data, SMAP is a microwave product. You may have some signal is not to the soil moisture, but with the canopy, right, the forest. So do you have some local soil moisture measurements?
Oh yes, exactly. Yes, we do have these measurements from the in situ and have the different depths. I didn't put it here, but we do already have made some comparisons. They also have some mismatches, but soil moisture is very heterogeneous, even at very small scales. And the HER data has 3 kilometers gray sizes and for the measurements from the point scale. But that's a very good question because especially in the forest with those high canopy areas, they should have a huge noises to those back scatterings for those SMAP data.
Yeah. Okay. Yeah. So another question you mentioned about the vertical profile of the leaf density and LAI for the canopy. Yeah, for this model. So, do you also have that profile data sets?
No, we don't have that profile data set yet, but I think Pat or maybe Jeremy has another project. They run those fast fuse data, and that models might produce some related to this live area density data at a 3-dimensional high resolution, maybe 1 meters live area density data.
Thank you.
Yeah, thanks for the talk. Actually, I have a question about the slide right before you showed. Yeah, so actually I'm curious. From these profiles, it looks like your model is not resolving that inversion well. So it's much weaker, near like 200 meters. If you look at potential temperature and specific humidity, it's much smoother in your WRF model. So I was wondering what is the vertical resolution, and if you are increasing vertical resolution near the level, it will improve that inversion, capping inversion above the boundary layer, because I think that will impact your larger simulation as well if you are using this as a forcing to that. So yeah, I think that might be related to the cloud simulation as well. So
Yes, thanks for the comments. Yeah, totally agree. And I also that region has the altitude of roughly 300 meters. Maybe that's the reason why the performance is not as good as that one. But that's a very good suggestions to increase the vertical grade size.
Yeah, if you can better resolve that inversion, I think the cloud simulation will be improved.
Okay,
Yes, yeah.
thank you. I'm gonna try that later.
Hello? So I wanted to check, because I didn't quite follow, so in the model only, do you know exactly what factors led to the initiation? What, did you say it was later in the day? What exactly occurred? Are you saying that it's the relative humidity being overestimated that caused the CI to occur later?
That could be one of the reasons, but also maybe the initial conditions of the soil moisture could also cause that regions. Because when the atmosphere demands less or more waters from the land surface, gonna cause those mismatches. So yeah, so the question is like we kind of like don't know exactly which is the main cause of this setup. Maybe we're gonna try to update or to improve the initial conditions and to see if they're gonna match the onset of the clouds.
Oh, okay, so just to confirm, so you found later that the latent heat, I guess, and sensible heat were overestimated as well, and that's why?
It depends on the land cover. For example, this S10, the second one, this site is located in the forest. And I think in the morning, the worth is slightly overestimated compared to this measurement because there's no clouds, and in measurements they have clouds here. But when the clouds existed, they have quite good matches afternoon. However, for this S30, I think maybe there's already clouds, but we don't have the measurements of the clouds at the S30 site. So they matched pretty well even in the early mornings here.
Okay.
But yeah, the other side is not good. So yes, it could be like it's a two-way like. At this moment, you don't know which one started first, like because there's clouds formed to cause these underestimations, or because the underestimation caused the later onset of the clouds.
Okay, yeah, and I just wanted to, I guess, recommend one thing. So you showed potential temperature, but I think in some cases, especially when you're talking about a lot of vapor coming from the soil, so and the plants, so I'd recommend using something like virtual potential temperature. And there's also a way that you can decompose that into the vapor, the sensible heat effect, the thermal effect, and also the vapor effect. And for buoyancy, for example, and you can, I think you might end up seeing not as much agreement.
Okay.
Possibly.
Yeah. Thanks.
Thank you.
Yeah.
I just throw it.
Yeah. It's durable enough. I guess, do you not have any questions online? Okay. Maybe just real quick to summarize, could you kind of give some motivation of the background of this sort of research? So what is the importance of doing these types of simulations?
Yes. So when the synoptic scale forcing is very weak, then all these processes, all the local climate was determined by just it's more like the forcing data, and also the land surface heterogeneous, different land covers. And currently in the COM, you just calculate the fluxes or the states for each type of the plant function types. Then you aggregate them based on the average mean. Then you get the grid scale values for that, for example, in the numerical weather predictions or for those climate models. However, the work I before showed that even you have the same mean value of the soil moisture, based on the parameterizations, if you have the same soil moisture, you should have the exactly same like liquid water passes. But because of those interactions or those complex processes within the canopy or within the boundary layers, they're gonna impact the process on the whole dormant areas. You get the different fluxes and the different states. So in these regions, there's a lot of forest, and the forest should have a lot of different heterogeneous in the different like leaf area index, the different plant heights, the different roughening lengths, the different soil moisture signs, and all those together will have influence the income radiations and have the different sensible land and heat fluxes and have the different motions. And also above and below the canopy, the atmosphere movement will impacted by the existence of those canopies here. So that's why we are doing here, like if we only focus on those period when it's just locally forced shallow convections. And this process is not very clear understandings at the moment. And this is the rest question that we want to answer based on this project.
Do you have any more questions in the room?
More of a comment, kind of echoing the first comment, just with as a caution with using SMAP soil moisture retrievals in forested areas. That I just kind of echo that. And some colleagues and I, we did a paper. We were looking at comparing SMAP soil moisture with WRF soil moisture with USCRN in situ soil moisture, and mostly in the west because we were interested in dust generation and things like that. We found that at least in the more arid regions, WRF tended to overestimate soil moisture, and that there were also some pretty significant disagreements between SMAP and USCRN. So, and I think we were, in that study, we were basically screening out and not using any retrievals over forested areas because we didn't trust the data.
Okay.
So just as a caution that SMAP, again, reiterating it's a caution that SMAP soil moisture retrievals over forested areas use with caution. So, but yeah, I think it's definitely an interesting area, and we need to, so I'm glad that you're looking into how looking at soil moisture heterogeneity and things like that impacts convection. I think this is an important area. So yeah, thanks for the talk.
Do you have any suggestions for the other data set for the?
There aren't great. Well, I mean, as you know, the SMAP satellite, as soon as it got up there, its best sensor failed.
Yes.
So we're not getting as good data as was designed or hoped for. But I mean, USCRN has fairly wide distribution of a lot of stations, but it's a whole bunch of points. And like you said, soil moisture is very highly locally heterogeneous.
Yes.
So how do you spread that? How do you spread those corrections out? Like if you maybe correct the SMAP with USCRN, that might be something to consider, although that gets into other cans of worms too. But yeah, just something to think about in these forested areas where you might be getting more of the canopy effect in the soil moisture retrieval.
Okay, thank you.
All right, if there's nothing else, let's thank our speaker one more time.